Chapter 7 review for test. Number 1, a 3-kilogram mass, as we're reading the problem, if we chunk it and identify and say, okay, this is my mass, is traveling in a circle of 0.2 meter radius, so here's my radius, with a speed of, so here's my speed, so already I see that I have the mass, I have the radius, and I have the speed. And when I write down my given, and remember that your FRQ paper, the back is scrap. There's only 15 questions like this that you're going to be doing, and some of them are conceptual that you're not going to be working out. So if it's a small problem like this that you're going to work out, go ahead and write it down on the back. Because when you're not sure what to do, when you write down your given and you write down what you want to find, it helps you to identify which equation you want to use. Okay? And luckily on the semester exam, you're going to have an equation sheet.
Really?
What is the centripetal acceleration? So now, centripetal acceleration is equal to v squared over r. So I actually don't need the mass. I would need the mass if I was finding the centripetal force, but I'm not. So it's just going to be 2 squared over 0.2. So 4 divided by 0.2. Now again, this is something that you could do in your head. One of the things is whenever you have a decimal like this in the denominator, you could just do pretend and move it over 1 and say, oh, this is 40 over 2, and you could say, oh, that's 20. So that's one of the tricks for doing division with decimals in your head. Because we can always make a mistake pressing the wrong button on our calculator, so you should always, something that's easy like this, just kind of eyeball it and check the answer in your head. And these are little tricks that are going to help you, not just for physics, but for any type of test like that. All right, number 2. If the velocity of a car traveling around a circular track doubles its centripetal acceleration. So I'm talking about centripetal acceleration. Whenever, this is standard type of question that they ask on a test like the SAT-2 in physics or something like that, a standardized test. So they just want to see, do you know how to manipulate an equation? So for number 2, we know the centripetal acceleration is v squared over r. And then it says what happens to the velocity. So if I rearrange the equation and say ACR is equal to v squared, if I double the velocity and it becomes 2v squared, it then becomes 4 times. So it's 4 times greater. So this is a typical type of question you see over and over again. It's basically, do I know the equation? But if you, instead of doing something like this in your head, if you write it out like this, it makes it a lot simpler. Number 3, the diagram below represents a ball undergoing uniform circular motion as it travels clockwise. So this is important, and they actually show the arrows that it's going this way. At the moment shown in the diagram, what are the correct directions of both the velocity and the centripetal acceleration of the ball? So the velocity always acts perpendicular. So here's my velocity. And then the acceleration always acts towards the center, so my acceleration is going to go this way. Okay? Let's say if they ask me for any other point. Well, for any other point, here's my velocity, here's my acceleration, here's my velocity, here's my acceleration, here's my velocity, here's my acceleration. So as it's going around, the velocity is always going to be perpendicular at that point, that one point only, and the acceleration always acts towards the center. So this is the type of question on the test that honestly should take you about 5 seconds to do. And most of the 5 seconds would be bubbling the answer. So this isn't one where you have to write any work or anything like that. Number 4. As the time taken for a car to make 1 lap around a circular track decreases, so this is going to decrease the centripetal acceleration. So I have to find the relationship between centripetal acceleration and the time it takes to go around the track, which is the period. Well, I know that centripetal acceleration is v squared over r, but if I look at that equation, I don't see period in it. Now another equation we learned is V is equal to 2 pi r over T. Now, earlier in class we had taken this equation and substituted it in here. I personally don't memorize that as another equation because I can substitute it in. I can say AC is V squared, which is 2 pi r over T squared over r. So when I multiply it all out, I get 4 pi squared r squared over T squared over r. And then what happens is this r there cancels with that. So centripetal acceleration is 4 pi squared r over T squared. Now I go back and I look at the question. The question says, as the time taken for a car to make one lap around the circular track decreases. So as this number gets smaller, what happens to this? Well, we see that this is in the denominator and they're inversely proportional. So as this gets smaller, this gets larger. So the answer is going to be increases. Number 5, the path of a satellite orbiting the Earth is best described as, so this is Kepler's first law of motion. Kepler's first law of motion says that the paths of the planets orbiting the sun are ellipses. So this is, again, another like 5-second, 10-second question. You don't have to do a calculation. You don't have to look at the formula. So we already have 2 like that. So even though we didn't work any of the problems on Kepler's laws, yes, we need to know Kepler's 3 laws of planetary motion for the test. Number 6, as the distance of a satellite from the Earth's surface increases, the time it takes the satellite to make one revolution increases. Now, we could look at the equation. We could look at V is equal to 2 pi r over T. Because remember, the time it takes the satellite to make one revolution, what is that called? That's the period, T. Okay? So if we say V is equal to 2 pi r over T, as the distance increases, then the time would decrease. All right. Let's look at the next one. Whoops. If object O is moving in a uniform circular motion around point P at a constant speed, which vector shown below represents the centripetal force? So there's one thing that I need to know for centripetal force. If something's going in a circle, the centripetal force always acts towards the center of the circle. So the only one that acts towards the center is going to be B. So again, this would be a question that takes about 5 or 10 seconds. Number 8, in the diagram represents the path taken by planet P as it moves in an elliptical orbit around the sun S. The time it takes it to go from point A to B is T1. The point it takes to go from C to D is, and this is the same. Now, before just memorizing, this is Kepler's second law of motion. And this is the equal area law. But what we explained before was that the equal area law has to do with conservation of energy. And conservation of energy, why is the time it takes to go from here to here the same as the time it takes from here to here? Because the total amount of energy remains the same. Over here, the Earth is farther from the sun, which means that the potential energy is greater than the kinetic energy. So because the potential energy is greater and the kinetic energy smaller, we know kinetic energy is what? 1/2 mv squared. So because the kinetic energy is smaller, that means the velocity is less, and that means it's going to be going slower. So it's going to take more time to go from here to here. On the other side here, we see that over here, it's closer to the sun. So because it's closer, the kinetic energy is greater than the potential energy. And again, kinetic energy is 1/2 mv squared, so it's going to be going faster. So it's going to go from here to here in the same amount of time. Okay? So this explains the equal area law. But again, this is Kepler's second law, equal areas and equal times. Now, probably in middle school, before you learn conservation of energy, you probably just memorize Kepler's second law. But instead of memorizing things, if you understand the concepts, then you remember it forever, and you're not just memorizing it for a test. Okay, the last question on the front says, in the diagrams below, P represents a planet and S represents the sun. Which best represents the path of the planet as it orbits the sun? Well, first of all, we said that planets orbit the sun in elliptical orbits. A and B, are these even ellipses? No, they're circles. So we're going to cross that out. Now, if you look at these models, P represents the planet, S represents the sun. Is the sun going around the Earth? No. So, besides this being a very quick question that you can do in a minute, it's very, very simple. This is stuff you learned in elementary school. Okay, but again, it has to do with Kepler's first law, that the planets are moving around the sun in elliptical orbits. All right, let's look at the next page. Now we have a couple of calculations here, some of them. So time to take out the calculator. Now again, this is where you really need to practice, because when we're using the universal Newtonian gravitational constant, it's an exponent. It's a negative exponent, and you need to make sure that you know how to put that correctly into your calculator. All right, number 10, two objects of equal mass are a fixed distance apart. If the mass of each object could be tripled, the gravitational force between the objects. So again, first I'm going to write down the equation. F of g is equal to big G, the universal Newtonian gravitational constant, m1, m2 divided by r squared. So it said if the mass of each object was tripled. So when I write my equation now, f of g is equal to g, but instead of m, I'm going to write 3m. Instead of m2, I'm going to write 3m over r squared. Now when I look at these two things, the only thing, this is the same, this is the same, the only difference is this and this. So 3 times 3 is 9, and the 9 is in the numerator, therefore it would be increased 9 times. This is the way you do these types of problems. You write the equation out, and then when they say, how does the variable change, you just write it in and you look at the difference. The more you write down on paper, the less likely you are to make a mistake. Don't try and do stuff like this in your head, because when you do it in your head, that's how you make a mistake. You write it down, and then there's not going to be a problem. Number 11, compared to the mass of an object at the surface of the Earth, the mass of the object a distance of 2 radii from the center of the Earth is the same, because the mass stays the same. Mass stays the same for all intents and purposes in this class. And we talked about that also. Number 12, the centers of two 15-kilogram spheres are separated by 3 meters. So again, we're chunking this, where we're saying this is the mass, this is the distance between them, and it says find the gravitational force. So F of G is equal to big G, m1, m2 over r squared. You don't have to memorize the universal Newtonian gravitational constant, big G, so 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times 15 times 15 divided by 3 squared. Now, let's look at how we're going to do this on our calculator. So on the calculator, I always go from right to left. You do it the way you understand. So I'm going to say 15 squared times 6.67 EE, and then I do 11 minus. So now I see that 6.67 times 10 to the negative 11. I do not press times 10. So you have to know this is the exponent button, EE, equals divided by 9 equals. So now I have this crazy long number, But if I want it in scientific notation, behind the number 5 it says SEI, so I press second, psi, and it says 1.66 times 10 to the negative 9. Okay? And now if I look at my answer choice, that's choice C. Number 13, as the mass of a body increases, the gravitational force. So again, you're going to look at the equation, F of G is equal to big G, M1, M2 over R squared. So it says if one of these masses increases, what happens to the gravitational force? This. Well, this is in the numerator. So if this gets bigger, this also gets bigger because these are directly proportional. So the answer is going to be increases. Number 14. If the distance between two masses were tripled, the gravitational force. So again, this is the same thing we're doing over and over. F of G is equal to G, M1, M2 over R squared. So now it says if the distance were tripled. So it's G, M1, M2 over 3R squared. So when I square this R, everything else is the same. The only difference is in the denominator, 3 squared is 9, so I have 9 in the denominator, so that's why it's 1/9. These are actually very simple, but you have to write down the equation. You don't do this in your head. And then the last one says, if the mass of one of two particles is doubled and the distance between them is doubled, now what happens to the force of attraction? So again, it's the same equation. I'm not even going to write it over. So now it says one of the masses is doubled. So now I'm going to double the first mass. And then it says the distance between them is doubled. So I'm going to double that. So now I'm going to look at what's the difference between my basic equation and here. So what happens is I have a 2 in the numerator. In the denominator, I have a 2 squared, which is 4, which would be 1/2. So that's why I see it's going to decrease. And if they ask me how much, I would say, it decreases by half. So this is the way that you do all these. And that's it.